Hello, Professor. We are Group Quad M, and for our project, we built a wildlife sightings application focused on aquatic species, specifically ray fin fishes. Our application allows users to search for different kinds of fishes based on their needs, and my colleague will be shedding more light upon the filters functionality in a moment. Meanwhile, in terms of our technology stack, on the back end, we use Fast API with Python for fast and clean API setup, and of course, along with MongoDB as our non-relational database due to its support for flexible schemas and powerful queries. We also use PyMongo and GridFS to manage and display fish images. On the front-end part, we use React with Vite for a smooth development experience and component-based design. We also tried to keep our styling lightweight by using plain CSS. For development tools, we use GitHub for collaboration and use an application called Postman for testing endpoints. We did all our coding in VS Code. My colleague Garima will go ahead and explain the process.
So we downloaded our dataset from the iNaturalist website, which had our dataset had approximately 100,000 image URLs. And initially we tried using this dataset as is and dynamically fetching the images. But this process was extremely slow on our earlier server. So we decided to download all the images to our local machine using a Python script, which totaled up to 13 GB even after compression, which created additional challenges in terms of upload time. So we used another Python script to populate our MongoDB database and successfully loaded all our data. That script begins by establishing a connection to the MongoDB server, and it also ensures that the database has a 2D sphere geospatial index for our location-based queries. It also reads the data from the CSV file and then constructs a MongoDB document. It converts all the latitude and longitude data points into a GeoSun point. And if an image URL is present, the script will check if the image already exists locally. If so, or after downloading it, the image's binary data will be stored directly within MongoDB using GridFS. To optimize the uploading process, the script inserts these documents into a collection in batches of 100. It also utilizes parallel processing for efficiency and provides progress updates until all the data and images are successfully uploaded. Moving on to bells and whistles.
So, one thing we did well was creating a clean, user-friendly interface where we focus on keeping it simple and easy to navigate, which really improves the overall experience. We are proud of our search filters that we added. Users can now quickly filter results by who made the observations and by date, making the searching faster and more precise. Our standout feature is the interactive map. Users can zoom in, select specific areas, and set a radius to explore data visually. So this can help to lead into a more precise and location-specific findings, making the data much more useful. And overall, the platform gives users powerful tools to explore and understand data in a smarter and more focused way. Moving on to the volume.
Starting with the volume of data, I ran count documents on our database and it returned with 122,000 records approximately, and it returned the same amount of images, meaning that each document had an image linked to it. And our database was specifically focused on ray-finned fishes, and you could search by the search query, you could search by the species name, the common name, or the scientific name, or even by any name that appears in or any word that appears in the description, and you would get a result set. In that result list, you can apply additional filters such as user login, by which user uploaded that document, date range to narrow down your search to a specific time frame, geolocation to focus on a particular area. In our current database, green sunfish was the most frequently recorded species. This was the query that we ran, and it returned the top 10 species, and greenfish was at the top. This was the same query, but with matching scientific names, and it was the same result set, but with the scientific name instead. And for the city in the US with the most number of recorded observations, we got the top 15 cities, and Orlando was at the top with 376 observations. So this is our website. So I could search by any keyword that I want. I'm searching fish. I'm clearing all the filters that I have, which would, if I clear all the filters and I search by the word fish, it returns me a huge number of documents, which is 111,000 documents. And I could filter by a geolocation. So I'm going to choose Orlando, as it was observed as the city with the most number of recording observations. I could increase the radius as I wish, and the highest number returned is 1,214. I could reduce the radius to narrow down my results. So these are the results that are returned to me. I could go to a singular document, and that would give me the image of the document, the description, and all the details. And also, I could add comments to a document. And if I go back and I go to the same record again, blue spotted sunfish, the comment would appear again. And I could, on top of the geospatial filter, I could add other filters such as date. If I want to only get records after 10/12/2024, I could, and this would return me records after 10/12/2024. And if I want the results narrowed down to a single day, I could do the same, and the end date and the start date and the end date as the same, which would give me just one result, which is a 10/12/2024 within Orlando, Florida. So I could also filter by username. So I could filter by this user, which returns me 4 records, which are uploaded by this user. I could also filter by part of a username. So if I just filter by guy, so a user with the guy in any part of their user name would be filtered, and I get 22 results. Sorry. So this guy, this user has the word guy in their username, and so it's returned. And we also have a dark mode feature in our website. So if users wish to browse in dark mode, they could do that.